Yeah, thanks everyone for coming to Igor's thesis talk. So this is going to be his master's thesis, and the title of the thesis is Predicting Human Trajectories by Learning and Matching Patterns.
Yep. All right, I guess I'll just start. Hello, everyone. Thank you so much for coming to my thesis talk. I really appreciate your time and interest. Today, I'll be presenting the research I've been spending the past 2 years on together with my supervisor, Dr. Jing Oh, predicting human trajectories by learning and matching patterns. And this is the outline of the presentation today. Introduction. For intro, let's take a look at this interesting application of robot technology. A suitcase robot replacing cane for blind people. This is actually a project that I worked on in CMU. It's a suitcase robot to help blind people navigate. So this robot can be very helpful to this people group. And for it to be useful, sometimes you need to navigate through populated areas. Other than this robot, there are many other robots that would also need to work closely with humans, like medical robot, service robot, delivery robot. But I guess, are robots capable of navigating through dense crowds very efficiently, safely, and naturally already? Unfortunately, we can't be that optimistic yet. And this is a robot I built in the first semester of my MSR study. It's called Rocky. And this is Rocky trying to navigate through a crowd in New Old Simon Hall, which is the place we all miss very much. As you can see, as people are walking by, Rocky had to stop a lot to wait for people to pass. Right? So overall, Rocky's motions just don't seem very efficient or natural, right? I guess the problem is that Rocky or the robots nowadays don't understand humans' intention and behaviors as well as we human understand each other, right? If the robot can somehow either implicitly or explicitly know where everyone in the scene is going to in the next couple seconds, it can probably predict, it can probably navigate a lot better, right? And that's the problem we're trying to solve here, is to predict human trajectories. For a number of people walking in a scene, given observations of everyone's history trajectory, we want to predict everyone's future trajectory. That's a more proper definition of the problem we're trying to solve here. Given everyone's history, we want to predict everyone's future trajectory. Yep. Now, for that, we have two intuitions, right? The first is when navigating in a crowd, our motions are affected by others' motions. This should be straightforward and easy to accept. Let's take a look at an example. This blue triangle is just walking this way from here to here to here to here. And this is his current location, right? What do we think the next location of this blue triangle is going to be? Without anyone else in the scene, I think he's probably just going to keep moving forward, right? Take that step. But if there is another person approaching the blue triangle from the left behind, then I think the blue triangle might take a step to the right to avoid this possible collision here, right? His future location has already been affected by other people in the scene. But let's further assume there's someone else here already. Then this blue triangle's next location is going to be probably there. He might want to slow down and wait a little bit for people to pass first and then move on. So this is what we mean by how others' motions can affect, can trigger how others' motions can affect our motions, right? And the second intuition is similar motions of others trigger similar reactions of ours. This is actually at the core of our idea. This is what we mean. The same scenario, but let's just move this person's trajectory just a little bit so that they are different. They're no longer the same, but they're similar, right? Now, at this new scenario, what do we expect the blue triangle's next location to be? Is it going to be much different than before? Probably not, because the blue's situation is still pretty much the same with before, right? So we think its next location is still going to be there. And that next location still seems very sensible given the new circumstances, right? That's what we mean by similar motions of others trigger similar reactions of ours. And further, if we can group these similar motions together into one, we can have the same strategy, the same reaction to respond to that. And for these groups in this work, it is referred as motion patterns. Motion patterns are essentially just trajectory segments which can be repetitively observed in real world. Right? They are trajectories. They take the form of trajectories. They're just shorter. They're trajectory segments, right? Motion patterns. Now, with the idea of patterns, this is our solution, social pack. Social pattern extraction convolution. Our model learns patterns and their corresponding reactions during training, and recognize patterns and responds with learned reactions during inference using convolution. So patterns will be learned and recognized from the input trajectories, and the learned reactions will be our prediction to the scene. That's introduction. And related works, we will review what have been proposed to tackle this problem of human trajectory prediction. Right? We will see some popular trend, and this is the first popular trend, the wide use of recurrent neural network or long short-term memory, LSTM. This is this is very popular. Using RN for this problem is very popular in this research community. And who can really blame us for that, right? Because trajectories are, in discrete world, which is what we're dealing with, are sequences of locations, right? They are sequential data. And for machine learning, whenever we see sequential data, RN is almost the go-to method for us to take. For it has some very nice properties, right? First, it can take arbitrarily long inputs. How it works is this LSTM will take an input at every time step. Right? T0, T1, T2 takes the input X, right? And use that input to update its internal hidden vector H. And from that H, you can get whatever you want, whatever information you need. So this T can be a variable. It does not need to be a fixed length input. Right? And the second nice property of it is LSTM has the potential, has the possibility to remember everything that it had seen in the past. It can, yeah, it has the, it just might not forget everything. For example, at time step T, this HT might still carry information from a long time ago, all the way from X0 and X1, no matter how large this T is. These two nice properties are very important for some problem domains. For example, natural language processing, right? If you want your model to understand or translate an article, obviously the article length is arbitrary. You can't expect our articles to be the same length, right? Secondly, by the model get to the bottom of the article, it still needs information from the beginning of the article, because the first sentence very likely sets the tone for the article or defines the context that the model needs to understand the later sentence correctly. So Rn's properties are put in good use in this case. However, trajectories are a very different kind of sequences. Right? Imagine we have two people walking in the scene, and this is their history trajectories that we observe. By the time they get to this place, this area, they're about to interact. They're about to walk past each other. For us to understand the interaction here, do we really need information from a long time ago? Probably not. Information from a long time ago seems no longer relevant. If anything, taking those into account might even negatively affect our understanding of this current scene. It's just like me walking in a hallway and meeting you who's walking towards me, right? We're about to pass by each other. For me to successfully navigate through the situation, I only need to know how you've been walking in the past maybe 5 seconds or 10 seconds. I don't need to know how you almost bumped into someone half an hour ago, or how you've been walking in the past whole hour. Only the recent past matters to our interaction at this local area. Information from too long time ago is no longer matters, right? And I guess that's why, I guess for this recent past, we don't want it to be arbitrarily long. It can very well be a fixed length thing, right? It can be 5 seconds or 10 seconds period of time, which we base our understanding and prediction on. If we can accept that, we can open up our problem to many good machine learning models instead of sticking to recurrent neural network. After all, recurrent neural network has some flaws of its own: vanishing exploding gradients, unstable difficult training, time memory consuming, and inefficient parameters, right? So in this work, we avoided using RN. In fact, we actually used the convolutional neural network, CNN. And the second popular trend is this mysterious polling layer. Here's an example of the model of social gang, which is a very popular work in this field. In the center is polling module. Polling layer is actually a very reasonable and well understood operation in convolutional neural networks, especially for image-related tasks. It's typically used for dimension reduction. For this input that is 4 by 4, after max poll, the output is only 2 by 2. A lot smaller, while still carrying the most important information that you might care about, right? And it's done by taking the maximum out of every little patch. Like this 20 is the maximum from this patch, 112 is the maximum of this patch. Right? And what are these numbers? They are the kernel responses to the input signal. Or they can be seen as the similarities between the input signal and the kernels. They are similarities. And comparing similarities and taking the maximum of similarities are all just very sensible practice. Whereas in the case of trajectory prediction, the social polling layer is typically used to aggregate other trajectories in latent space. So for us to predict for this blue triangle, we need to aggregate all the information that we know about the other pedestrians, right? And the typical approach is like this. Imagine we have 3 trajectories, and we use LSTM to encode them one by one. Right? So this trajectory is encoded as this embedding vector, and this trajectory is encoded as this vector, and that. And then we stack them together, takes the maximum out of the 3 for every entry at this vector to get a vector that's the same shape with any of these 3, but carries the maximum value out of these three. This is how social pooling layer solves the problem we just talked about, information aggregation. But we don't understand this latent representation very well. LSTM, the model does, but we humans don't. We don't know what those numbers mean physically. And before we understand them, how do we know what maximum operation means? When we take maximum, is being large in this vector even a good thing? And what does being large mean after all, right? And also, could there be some dependency between neighboring entries? If there is, taking one entry because it's max out of the vector is breaking that possible dependency. So as you can tell, I don't feel great about this practice. So if possible, I would like to avoid using this, or to use it in a space that we have some understanding about, that we can justify, right? And the third trend is a somewhat reasonable choice, which is instead of processing every trajectory as sequence, some researchers model the whole scene as a graph where every pedestrian is a node. And along this direction, there are works like Social Attention, authored by actually our lab, Aniru Vanula and Dr. Jean Oh, and also the new state-of-art Social STG CNN from CVPR 2020. I believe graph presentation is a reasonable and promising direction to pursue. Right, and now we will compare our social pack with existing methods to highlight some features. First, we used convolutional neural network CNN instead of RNN, such that our latent space is actually explainable, can be understood by humans now, such that when we use social pooling layer, that practice is no longer obscure. And the achievements of our approach is we reached the best performance in terms of common metrics. But most importantly, our model has better transparency and better explainability. That's the intro. And now, that's the related works. And now let's take a deep look at the method, social pack. We will keep looking at this example scenario. I know we said the problem is to predict for everyone's future trajectory, but in reality, let's predict for one person at a time. Because if we can predict for one person, we can just take turns to predict for all people. Yep, when we are predicting for this blue pedestrian, we actually converge the coordinates to its egocentric view, such that its current location is at the origin and it's facing the positive direction of the x-axis. And the other pedestrian trajectories are also converted accordingly. This is to reduce the possible redundancies in the learned patterns. If we're predicting for the green or purple, we also shift coordinates. And now, if we're predicting for this agent, we will call that target agent. And all other agents will be called context agents because they provide this social context for our target agent. Right? Understanding the context is important for us to predict. And now we can sketch out the diagram for our model. We have target trajectory of the target agent. And for M agents in the scene, we have M-1 context agents. Okay? And we will encode this target trajectory into some target embedding. And also encode all of these context trajectories into a fixed shape of social context embedding. And then concatenate them together, feed them into this multi-layer perceptron, and output a future location, one-step location of the target agent. And the error of this next step location prediction will guide the training. Here, we're only predicting one location at a time. That's because if we can predict the next step location, we can always use that prediction as if it's the latest observation and append it to the history trajectory and further predict for the next location. So it's kind of like a rollout. If we can predict for one location, we can keep using that to predict and eventually get the whole trajectory. And that's how we use location predictor to predict trajectories. In this model, the tricky part will be here. We have m-1 context trajectories, but the output should somehow be a fixed shape thing. I guess the solution is actually very similar to the social pooling layer that we've seen in the related work section. We are doing that too. So there will be a social polling layer, but we use CNN to encode these trajectories so that we can justify the use of social polling. Right. Now let's look at the algorithm itself. These patterns that we keep talking about should be learned from real world data, right? At this point, we don't know them yet. But let's pretend that we do know them so that we can walk through the algorithm, right? Let's say there are only these 12 patterns that we care about. This target agent only care about these kinds of motions surrounding him. And we will represent every pattern with two locations discretely, right? So 2 points represents a pattern here. Let's put a trajectory there to see how we can encode this trajectory with the help of motion patterns. Now the model will compute the similarities between every pattern with the trajectory. So if they are similar, they get a higher number. If they are far in terms of location and also direction, not the same, they will just be assigned for a smaller number. And these 12 numbers are similarity scores of all the motion patterns. By knowing these numbers, we can actually have a pretty good idea about how this trajectory is, right? So these 12 numbers will be stacked to form a vector, and we use that vector as the trajectory embedding to represent this trajectory. Again, these patterns will actually be learned from data eventually. Another example, we can similarly encode the green trajectory. Now, we have two trajectory embeddings. We're about to merge them together, right? Aggregate them together with social pooling layer with some confidence. Confidence is because we do know what these numbers are. They are similarities. Comparing similarities, taking the maximum of similarities is reasonable. And by overlaying them on top of each other and taking maximum, we get this social context embedding, which is also 1 by 12. So we just turn a 2 by 12 tensor into a 1 by 12 vector, right? And this context embedding does convey the information of social context pretty well. Even now the trajectories are removed from the scene, right? But by looking at these numbers, we still have a pretty good understanding about the social context that this blue triangle is in. There must be someone walking towards it from the left behind, and someone else walking in this area along this direction. Right. So if we understand the algorithm intuitively now, hopefully, let's take a look at the mathematical definition. Imagine we have m pedestrians, m agents, and denote th as history length, and tf minus th as the prediction length. So from 1 to th, well, that will be the history. Th plus 1 to tf will be the future prediction. At time t, the agent m's location will be smt, and s is a location. And m's history trajectory is a sequence of locations, right? It's sequence defined over these timestamps. And the all history trajectories is just a set of trajectories. Trajectory corresponding to all agents, right? Given all history trajectories, 1 to th, we want to predict all future trajectories, th plus 1 to f. And for simplifying the problem, we, like we discussed earlier, we don't predict for everyone's future trajectory at the same time. We predict for one agent at a time. So instead of predicting the whole set, we predict one trajectory at a time, right? And instead of predicting the whole trajectory, we predict one step location at a time. So we only predict the location for th plus 1 instead of the full trajectory. Because again, we can do rollout to get the trajectory. And by doing this to all agents, we can get all agents' future trajectory. And that's how the problem is simplified to a location predictor. Now, pattern extraction convolution. So imagine we have n of those motion patterns. In the example we just had, this n was 12, right? The jth pattern, pj, should be defined as a sequence of locations. So it's also a sequence of locations, right? It takes the form of trajectories. And j is between 1 and n. Now, if we have these patterns, this is how we encode trajectories into embedding. The embedding will just be the result of convolution between trajectory and patterns. And this is just the convolution. But very importantly, this convolution operator is actually L2 difference instead of correlation in conventional CNN. So if you use a CNN in standard machine learning toolkit like PyTorch or TensorFlow, the operator in those CNNs are actually correlation, non-normalized correlation, which essentially is just dot product. But here we're proposing a new convolution operator because let's take this toy example to look at this toy example, right? This is the trajectory. It's defined as two locations, 10, 1 and 21. And this is one motion pattern, and this is another motion pattern, right? This motion pattern is farther, P1 is farther from the origin. So value-wise, it's larger, right? Intuitively, if you just look at this graph, we can say the similarities between these two should be higher than similarity between this trajectory and P1. But if we use correlation as the similarity measure, it will actually tell you they are less similar than them. This is because the correlation, essentially implemented as dot product in standard CNN, the value is affected not only by the similarities, but also affected by the absolute magnitude of the patterns of the kernels. And that's not what we want. We want the similarity measure to be only affected by the similarity, right? That's why we say correlation is not a good similarity measure for our case. Now let's refine the new operator a little bit, because the range of this output of this L2 difference is non-negative, is 0 to infinity. So let's introduce a log function to rearrange that back to the whole R, because the output of a neuron should be over the whole R. And also let's introduce this lambdas to scale the output. This is because in conventional CNN, the kernel magnitude controls this degree of freedom. But now our kernel patterns are constrained by how the real trajectories are. So we lost that degree of freedom. By bringing that back in, we can have this output to better interact with the non-linearity in the later activation functions. So this lambda is pretty important. The trainable parameters in this convolution are biases and patterns. They are really just the kernels in the CNN sense. And also these lambdas. These lambdas is something that typical CNN don't have. They don't need to have. This is something of our own. These values are trainable. Now we can fill in the content of this location predictor. Target trajectory, and we will encode target trajectory with one layer of pattern extraction convolution and a few layers of typical CNNs to get this omega m as embedding. And similarly, we use another network which takes very similar structure to encode all the context trajectories into context embeddings, omega 1, 2, all the way to m, right? And we use the social context pooling, max pool over this direction to aggregate all of these embeddings into one omega bar. And then we concatenate omega m and omega bar, feed them into this multi-layer perceptual location triple later to get the future location of the target agent. We're almost done. And this output is an exact location, which is not really ideal because real world is full of stochasticity, full of randomness. If we look at this scene, we can say, yeah, the location might be there, but also it could be there too. This location is pretty plausible as well. So really, the future location should be modeled as a probability distribution instead of one deterministic value. A natural choice is just Gaussian distribution and has its peak at this most plausible location, and the probability of nearby location just kind of drops. Further, this future location might actually be multi-model. This is plausible, right? And this is probably not so much. You don't want to be so close to the other people. But I think this area is also very likely to be the next location as well. So this green person might just take a step to the left. So he might have more than one peak. And Gaussian mixture model in this case is actually a better choice. So essentially, it's a combination of a few Gaussian models with weights corresponding to each one. So now let's change the output of the model to parameters that can define a bivariate Gaussian mixture model. This is the whole network. For training, we always take one step only. So we don't reuse our own prediction to further predict for training, during training. So during training, TF is always TH plus 1. So the future trajectory is really just one step, right? That's for training. And the loss is just log likelihood. And for inference, we do roll out to get trajectory. That's method. And now let's take a look at some interesting results. The metrics we use are actually also very common in this research field. They're average and final displacement area. The ADE is just defined as the L2 difference between the predicted trajectory and the ground truth trajectory averaged over time and averaged over the number of agents. And FDE is just the L2 difference between final locations instead of all locations in the trajectory, right? And for ADE, our models do have best performances compared to others, or at least comparable to the best, right? And FDE, qualitatively, here are some plots of the trajectories. The solid lines are history observations, and the dotted lines are futures. Right? The round dots are future truth, ground truth, and stars are future predictions. And you can see there are some faded star trajectories. That is because whenever we predict with our model, the model outputs 20 future trajectories at once. And we're only highlighting the best out of those 20. This is a standard practice for this problem. And as we can see, the predictions look pretty close to the ground truth and all very reasonable, even when the trajectories are not necessarily linear. There's some more. Right. And now let's visualize some patterns. And these are the pattern examples I showed you earlier. But the patterns learned from real data, of course, don't look like this. They look like this, right? These are 100 patterns learned from real data. And this triangle is just the target agent. Every arrow is defined by 2 points to represent a motion pattern. And here I also want to show how our model is, the training is robust. On the left, there are 2 different pattern initializations, but after training, they converged to something very similar. Also, let's also visualize the decision-making process, because we've been claiming the model is transparent, and explainable, right? So this blue triangle is the target trajectory, and the others are just context trajectories. There are 8 time steps, so 7 intervals, 7 segments. And we'll only take a look at the 4th and 5th, 6th and 7th segments of the trajectory, right? And there are 100 motion patterns at every plot, and the color of these patterns just indicate how much this pattern is present in this current scene, how much similarities are found between the pattern and the input trajectories. So if you look at this segment, these patterns and this area are heated, and this segment caused these patterns to respond, right? Similarities are found there, and similarities are found there, and the second last segment, and the last segment, right? So again, the colors are just the similarity scores of the patterns. So the prediction of the blue triangle is really based on the values of these patterns. And also the algorithm is actually incorporated as part of the social navigation simulator already to simulate human pedestrians. This simulator is implemented by our lab mate, Sam Shum, to train and evaluate social navigation algorithms. And also in the past year, Dr. Jean Oh and I and some other researchers co-authored a survey paper on social navigation, and it's submitted to a journal, and it's also available on our archive. So if you're interested, you can take a look. Future directions. In the future, we might consider input observations as noisy. Right now, we just assume all the inputs are all accurate and reliable. In reality, of course, that's not always true. Further, we can handle those uncertainties in the inputs and also uncertainties in the outputs caused by inaccurate model or other factors with Bayesian learning. And also we can expand social pack to other motions. Right now, it only handles human motions, right? But I believe it has the potential to also work for aircrafts, vehicles, and ships. And conclusions. Social pack achieved best performance in terms of common metrics, right? And it avoids the obscurity in information aggregation step, social pooling layer, that was present in the previous work. The proposed pack as a basic operator has the potential to learn and recognize patterns from data in other application domains as well, like natural language processing or image, instead of only trajectory domain. Right? And lastly, this study further challenges the community to re-examine the use of RNN in sequential data learning tasks. That's all of my presentation. And let me have some time to make acknowledgements. There are so many people that I need to be forever thankful for in this journey. Dr. Jean Oh, I wouldn't be here. This work wouldn't be possible without her continuous trust, support, and guidance. John, Heather, Jay, for being on my thesis committee, taking their time to advise and assess my work. I need to thank Red, John, Chris, Chieko for offering me staff positions for me to stay in CMU when I keep losing positions during various circumstances. I also need to thank G and my lab mates, Sam, Advai, Felix, Brandon, Xinjie, and many others for helping me with my research and projects. And I need to thank my parents for all of their sacrifice and love for me. I also need to thank my roommates and best friends in Pittsburgh, David and Allison. And also need to thank my friends from Northway Church and small group for all the good time, all the prayers, and emotional spiritual support. Lastly, I need to give all the credits to my creator, God, for making everything possible for all that I have. That is my presentation, and here's time for Q&A. Thank you.
Okay. Oops. Hey, thank you for the wonderful presentation, Hugo. So,
thank you.
All right. So and since you forgot to include the reference to your journal article, I posted on the chat.
Right. Yep.
This work has been published in a journal. So.
Yep.
So we will just follow the customary order. So we will take questions from the committee first. So how about we start with Jay? Jay, are you there? Maybe Jay stepped up. Okay, Heather, would you like to go first?
Sure, and I apologize. My video was working earlier in this meeting and now it is not, and it won't start. So I have no video.
Oh, yeah, mine also stopped. I think it's the network issue. So yeah.
Okay, yeah, I don't know. So on the results for comparing against, I guess it was different data sets, the Zara 1 and Zara 2, this was a table of results that you had. It looks like you didn't do so well on the Zara 1 and Zara 2. Can you speak to that? What is different about these data sets? What that made other methods work better than yours for those data sets?
So these data sets each have their own special characteristics. And I think Zara 1 and Zara 2 are probably less dense compared to especially university data set. And the motions there are more linear than university data set. So you might see more of trajectories just going in a straight line instead of having complex behaviors. So the easier the motions, the easier the ground truth is, the better for the model to give good performance. I think maybe that's why other methods perform better. But I guess after all, the fundamental the mechanism these models based on are vastly different. So some parts of the model might favor some part of the data set. And I think that's what we're seeing here.
Okay, so you think there's maybe not as much social context just in those videos where your model does especially well with social context?
I guess I wanted to say the behavior in those data sets might not be that challenging. So if you have models that don't capture social context as well, it can still give good enough results.
Just to add to that, among these data sets, the university set has the most exciting kind of social interaction, and all the other data sets are kind of dull. They just a few people walking back and forth. So
right.
Okay. All right. I assume we're going through one question at a time from each member and then circling around again, or?
I think if you have more questions, I think you can continue. Maybe there's follow-up questions.
Okay. So for this isn't quite a follow-up question, but the noise modeling, you mentioned, at least in the version of the thesis document that I read, that you can model it as Gaussian or using a neural net. Can you explain how you might expect your input trajectories, the error in your input trajectories, to be different than Gaussian?
Are you referring to the future directions?
Yeah, future directions.
Okay. Okay.
Sorry.
So Gaussian is one way to model the noise, but Gaussian carries using Gaussian has to force we make some assumptions about the noise, right? Where if we have a function that has very high flexibility, like a neural net, and takes the input as the input trajectories and output as the noise, we can essentially use the neural net as a function to approximate the real noise that are present in the input. That's, I guess, what I meant in the thesis document.
Yeah, I guess for a model of a sensor, say that's interacting with a wall or interacting with whatever. So there's probably some Gaussian noise around the actual distance to the target. And then there's also a chance of getting a like no return at all. So that doesn't fit in your Gaussian model. So that's what I was kind of pushing at it, like, what are the elements of our uncertainty about human trajectories that don't fit?
That's right. Yeah, there are many types of noise that don't don't necessarily fit in the paradigm of Gaussian.
Do you have any examples of that?
Currently, no, because the data we're using are actually not gathered by ourselves.
Okay, so you don't know how far off it is from the actual, like the
Yes.
the trajectory. You don't have the ground truth trajectory. You just have here's what somebody told me the trajectory is.
That's right.
Okay.
Yep. Thank you.
Hi.
Hey, hi, Jay.
Hey, sorry for joining late. My vaccine appointment took longer than I thought.
Right. Okay.
So yeah, I'll probably take a look at the presentation later on, but just had a quick question on the metrics that you have been using.
Mm-hmm.
Do you think these, I know these metrics are pretty popular when it comes to both, I mean, in general trajectory prediction domain, but do you think these metrics effectively capture what we are trying to do with the prediction? And if not, do you think there are better metrics? And if you have any suggestions on the kind of metrics that we should be using?
Yeah, these metrics definitely have their flaws. There are, I believe there should be better metrics. But I guess for us to publish our work, for it to be recognized by the research community, we have to use something that's widely respected and recognized and accepted. And this is almost the only choice that we're left with, ADE and FDE. Better metrics, I believe there should be. For example, if we claim the future trajectories is a probabilistic thing, then there should be some metrics that's based on, that's distribution based. For that, there's a survey paper on human trajectory prediction. I can point you to later. In that work, they cover more metrics, but this is what we're using in this work.
Okay, thank you.
Okay. Jay, do you have any other questions before we move on to John?
I think I'm good for now. Thank you.
Okay.
Thanks.
Right. Then John.
Great, thanks,
next.
Jim. Eagle, nice job. It's great
Thank
to
you.
see you've done so well. I'm really pleased. Let's see. One thing I wanted to get clarification on the thing that Heather asked about. You said you don't have the ground truth, but I would have thought you had some kind of, I mean, obviously you have ground truth in your equations there. I thought you would have had a sequence that you're looking at with video or something like that, and you can figure out what the ground truth is from that. Did I misunderstand?
Like I said, the data set are annotated already. I think it's a terminology issue. It comes down to what we consider ground truth is. If we think ground truth are the truth of the world, then no engineering techniques can actually capture that, right? But if we believe the accurate annotation of the video is good enough and take that as ground truth, then yes, we do have ground truth.
Okay, and annotation is just putting a bounding box around someone and then finding a coordinate from that. Is that?
Yes.
Okay. Good. Then one thing I was wondering was, what is the prediction horizon? I don't care about the exact number necessarily, but I was just wondering if you could comment on what kind of prediction horizon makes sense, what you're using, either in terms of time or distance, and then whether or not if you vary the prediction horizon, you see differences in the comparisons between different methods.
Yes. Let me get to the result table actually. When you say horizon, did you mean input or output, or history or prediction?
I meant the prediction.
Okay. So in our problem, the history, the observation is always 8 time steps. Each time step is 0.4 seconds. So 3.2 seconds of history.
Mm-hmm.
And the output is either 8 time steps or 12. So either 3.2 seconds or 4.8 seconds.
Mhm.
And when we look at different lengths of different horizons of the future prediction, we do see different performances. Actually, the newer models do better with longer term prediction. Actually, what you're seeing here is the so-called long term prediction, which is the 12 time steps, 4.8 seconds one. And
Right.
our model does pretty good job there. When it goes to, I don't have the result here ready for you, but when it goes to the shorter prediction, I guess the performance difference between models don't seem that big, because after all, if you only look at short trajectories, they can easily be modeled as like a straight line, and you can still get pretty good result out of that.
Yeah. Yeah, that makes sense. I guess for that one that Heather had asked about, I would have expected possibly, based on your answer as to why a couple of the other methods did better on a data set that has more linear trajectories. Well, I guess if they're purely linear, like in the extreme, if they were entirely linear, then that one would have a perfect score, and perhaps you'd be able to have a perfect score as well, although maybe you'd have a bias towards looking for nonlinearity that would cause you to not be as good. But I'm just wondering if there's some sweet spot in terms of the look ahead distance or the prediction horizon that causes yours to be better even in that particular case where it was not, according to this 12-step. I don't know. The other thing I was wondering was, you mentioned application to other vehicles at the end and aircraft and that kind of thing, but which is interesting to me because certainly it'd be interesting to apply it to autonomous driving. And I'd like to hear what you think about that in general. One thing specifically I was wondering about was, you said that you felt like one of the reasons that you could use a CNN rather than an RNN was that, well, I interpreted it as that you have a fairly small velocity range for human beings, whereas that won't be true for cars or aircraft. So if you have a big variation in the velocity over time, is that going to create problems for your method?
Yeah, that is one thing. But I guess the bigger point I was making to justify my choice of CNN over RNN is that no matter how long your interest is in terms of the history, it can be a constant number. So with smaller velocity, maybe we only look at 5 seconds. If it's fast, then we can look at the past minute or the past 2 minutes. But no matter what it is, it can be it doesn't need to be arbitrarily long. We don't need to store information all the way from the beginning when it becomes available. We can safely discard, if we accept this stance, of course. If we accept this, we can safely discard information when they have passed our interest region, interest window. I guess for cars, I don't have a good idea about what that number should be, but in this work, I just want to argue that it can be a fixed number. And I guess to apply this to vehicles case, vehicles' motions are very different than humans' motions. We see a lot of from left to right movement. Humans shift horizontally, kind of, in a crowd easily, but cars have very limited motions. In that, I guess we can't really do the pattern learning in the Euclidean space anymore. Maybe we need to create another space that works for vehicles' motion and do patterns and apply similar idea of patterns there.
Yeah. Okay.
So you're talking.
Right. Sorry, go ahead, Heather.
I was just, you're talking specifically about vehicles in on roads with lanes where they're restricted.
That's right. Yeah, that was what I was talking about. Yeah.
Yeah, what could be a little bit more similar, maybe, although it depends on the extent to which people are following the pseudo lanes in a parking lot, but it might be a parking lot which sometimes turns into a free-for-all with people roving around the parking lot in directions they shouldn't be going and that kind of thing.
Yep.
Last question is, and I mentioned this to you in email, Rocky. When you talked about Rocky briefly, I had to let my dog in at the beginning, so I missed about 30 seconds or so. But what kind of validation, if any, have you done with Rocky on this sort of thing? Like, have you implemented the algorithm on Rocky, or what role does Rocky play here?
I think it's being implemented on Rocky right now. The problem is when we were about to do something about Rocky and do real robot experiment, COVID pandemic started.
Yeah.
We lost the people that we can experiment with. So
Right.
we almost paused that and started doing things with more data and simulation.
I see. Okay. All right. Sounds good. That's it for me. Thank you.
Thank you so much.
Yeah, just to add one thing. So, for this framing, it's a short-term prediction. So the reason why Eagle wants to look at maybe just a few immediate past trajectory is because this is for the local planning rather than the global planning that requires looking at a longer horizon, like a past and the future.
Mhm.
So there is more reactive part of the planning. So,
Yep. Good.
Right.
and then, to add to that, we had a big plan for the real robotic experiment last year, which was totally ruined. So, but in the end, all in all, worked well. So Eagle also got to do a lot of work with the simulation environment. So we will have more results on that later too.
Good.
So
Has Rocky gotten his
okay.
vaccine already?
Oh, yeah, that's funny. So yeah, Rocky is currently in Sam's apartment. So we did a kind of mini experiment with the single person with the social distancing, of course. So
Great.
okay. So yeah. So any other questions from John, Heather, Jay?
Nothing for me.
I
Okay.
do have one more. How do you decide how many motion patterns to train?
Very quickly, am I still sharing the screen? Do you see the
Yeah,
slides?
yes, I
Okay.
still see social robot Rocky.
Okay. I guess it's through ablation study. I sort of need to take a guess in the beginning based on my understanding of interaction in the crowd to guess how many patterns that I want to care about. Because again, patterns should be something that intuitively makes sense to algorithm designers. So I took a guess in the beginning and then experimented with a few possible values and eventually came to this 100 number.
Okay, so you just tried some different values and 100 seemed to work in your experiments.
Yeah, it's almost good enough. Like increasing the number of patterns don't increase the performance in terms of ADE and FDE anymore. So
Okay.
we kind of just stopped there.
Okay, thank you.
Yeah, thank you so much.
Yeah, I just had a follow-up on that. So I'd just like to combine Heather and John's question here, where these patterns that you experimented with are pretty specific to the pedestrian sector. And you definitely in your future work talk about the fact that this specific method is extensible to say driverless vehicles. What do you think would be the major changes in the kind of primitive engineering that you have to do? And do you think, because motion primitives have been around for some time, do you think you can somehow look at that paradigm of those predefined motion primitives to kind of aid in this sort of a prediction for driverless vehicles?
Yeah, I don't have a very good answer for that, I guess. I have not thought extensively about how to apply this to other areas. But like I said earlier, it would definitely take a different space than Euclidean space. We probably need to create a space that makes sense for aircraft or vehicles motions. Motion primitives will be very helpful for inspirations, I guess, in that area. But no matter what space we're in, I guess the idea of finding patterns in that representation space and recognize them respond to that with learned reactions during inference is still applicable, I believe. Yeah.
So using these patterns is similar to kind of using prior patterns. So in a very abstract level, you could think, for instance, in like object detection, people have used anchor boxes, which is kind of remembering typical locations in the image space. So you can kind of view this idea as a trajectory patterns, pattern prior. So speaking of that, my question is actually related to Heather's earlier question about the size of the pattern, the number of patterns. So to me, it seems like there is let's say there is an ideal number of patterns that you need that can handle different levels of density in the crowd. So then the algorithm has to be scalable in the number of patterns. So can you comment on your algorithm's scalability in terms of the number of patterns?
Right. You are right. If the crowd gets more dense, maybe we do need more patterns. This 100 number is selected experimentally with the data set that are available to us at this moment. If the data set happens to be more dense, then maybe we do need to increase this number. And in terms of scalability of the model, it does scale pretty well. When this number of patterns increases, the inference time does increase, but not by a lot. I guess it has the potential to work for more patterns, but at this moment, for the data set we're choosing to use, it was not necessary to have more patterns, but it does scale. Okay.
And then a related question is, so I think you had that experiment earlier on. So suppose you have a very, very dense, but kind of uniformly distributed patterns that you can kind of predefine. So like you do like 10 degrees from each side and so on.
Yep.
So like something like the first one here, but in a much dense representation. Then compared to that kind of uniform pattern, did you have the results that yours learned patterns are better than those? Or if you remember,
that was the result. Yes, it will take me a while to find it. It's not ready at hand. So that kind of a dense, uniformly distributed pattern, and if we freeze that, we don't let the model improve on that, the performance is actually pretty bad. And if we does allow the model to unfreeze the weights and learn, it eventually comes down to something similar to this again, and gives similar performance to this.
I see. So yeah, that's interesting because that's kind of consistent with what computer vision people have found with the grid versus these anchor boxes.
Yep.
Right. Okay, thank you. And if there are no other questions from the committee, we can open up to the general audience for questions.
Yeah.
Anyone have questions?
Yeah, Eagle, I had a question.
Right.
Go ahead, John.
First of all, great talk. One thing that I was a little confused about, or it's more of like a clarifying question, is you use the trajectory prediction to find the next position of a person. You find like their discrete position, and then you create a Gaussian distribution around that. Is that correct?
Yes.
Okay.
Well,
so
let me just make it more accurate, actually. not to find exact location first and create a Gaussian around that. The output of the model is a Gaussian.
Okay.
Right.
So the output of the model would also include the other Gaussian distributions in the Gaussian mixture model?
Yes.
Okay, I see. Okay, thank you.
No problem.
Okay. Any other questions? Okay, then thanks again for a nice presentation, Eagle, and also thanks everyone for joining.
Thank you all.
And at this point, I think we will just have a committee meeting separately,
Okay.
and then so how should?
Yeah, well, if people want to stop by and say hi, I sent a Zoom link to the chat. We can all leave this room and go to that and hang out there. And I'll be there until Jean, you asked me to come back. I'll just leave.
Yeah, I'll send you a Slack message when we are done.
Okay. Yeah. Well, if
Okay.
nothing else, I'll see if anyone interested in the other Zoom room.
Yeah. Go have fun.